Hello and welcome to this video where we take a look at a problem about vapor-liquid equilibrium and how we can use Python in order to solve a specific type of vapor-liquid equilibrium problem. So let's take a look at the problem first. So what we have here is that we've been given Raoult's law. We've been given a mixture of benzene and toluene, which have been allowed to get to equilibrium. They both exist as solid and gases at equilibrium, and thus we've also been given Raoult's law for both benzene and toluene, which is basically the mole fraction of one component in the gas phase multiplied by the pressure is equal to the mole fraction of that component in liquid multiplied by its saturation pressure. Likewise, we've also been given the Antoine equation, which is as such. The different constants A, B, and C for both benzene and toluene is also given. Now, what the problem asks us to do is that it tells us the mole fraction of benzene in the vapor phase, and it gives us the pressure, and asks us to find the mole fraction of benzene in the liquid form, as well as the temperature that it exists at. So let's take a look at how we're going to do that in Python. So first of all, what I'm going to do is I'm going to import NumPy, and I'm also going to import from the scipy.optimize module, I'm going to import fsolve. Basically, these are the things that I'll actually need in order to solve this problem. First of all, let's save everything we have as variables. So first of all, we've been given the mole fraction of benzene in the vapor phase as 0.33. Now we know that mole fraction of toluene in the gas phase should be 1 minus the mole fraction of benzene in the gas phase, because the total mole fraction has to add up to 1. Next thing we've been given is the pressure. So that's 120 kilopascals. And yeah, that's about all we've been given. I'm also going to store all of these Antoine constants for benzene and toluene because we will be needing it later on. So I'm going to save both of these as two different arrays. An array will have all A, B, and C values for benzene, and the other one will have the same values for toluene. So let's call the first one ACB for Antoine constants of benzene, and I'll save that as this: 13.7819, comma 2726.81, comma 217.572. Likewise, Antoine constants of toluene is equal to 13.9320, 3056.96, and 217.625. Now we've got that, so let's execute that. Now, the first thing I want to do is actually calculate the saturation pressure. So I'm going to write that down as a function. What I want to do is I want to write this particular equation as a function. So first, for benzene, let's do that for benzene. Define P saturation of B, and we'll probably take the temperature as the input. And what we want it to return is so what this if I take this natural log to the other side, it's going to become the e raised to the power of this whole entire term. So what that looks like is np.exp brackets, and we have a, so that would be ACB 0. So that would be the first value of this Antoine constants of B array, and we subtract that from B, which is ACB1, and we divide that by the sum of the temperature and the constant C. So ACB2. So we have that to calculate the saturation temperature of benzene. Now we also create another function which is exactly the same, except it's going to be for toluene. So we have the saturation pressure of toluene, ACT, that change here as well, and we have two functions that can calculate the saturation pressures of benzene and toluene. Now what we want to do is we want to create a function that calculates our Raoult's law. So what I want to do with this function is that I want to bring everything to one side and have the other side be 0. And one thing we notice here is that we already know what the mole fraction of benzene is in the vapor phase. We know the mole fraction of toluene in the vapor phase. We know that our pressure is 120. And then we already know how to calculate the saturation pressure of both benzene and toluene, assuming that we know what the temperature is. What we don't know is the mole fraction of benzene in the liquid phase and the mole fraction of toluene in the liquid phase. So right now we have 3 unknowns, XB, XT, and T. But we only have 2 equations, which is our 2 equations of the Raoult's law. But now what we remember is that the sum of XB and XT, the mole fractions of benzene and toluene in the liquid phase, is always equal to 1. So that is our 3rd equation. Now we have 3 independent equations and 3 variables. So this problem is now actually solvable. So what I'm going to do is I'm going to write a function that includes all 3 of these independent equations, and I'll represent them as residuals. And what I'll do is I will use SciPy solver in order to solve those 3 functions. So let's take a look at how we'll do that. So first of all, let's define our function as f, and let's say it takes z as an input. Define f, z as input. So our first equation, let's say, is f0, and this is equal to xb plus xt minus 1. Basically, all of these equations should be equal to 0, even though I'm storing them in a variable like f0. So xb plus xt should always be equal to 1, and I subtract 1 from there in order to make this term 0. Next thing, our next function, f1, is the product of yb times pressure minus, we have xb times P saturation temperature of B, and it takes temperature as the input. Finally, we have our Raoult's law for toluene as well, where we basically only changed the benzene to a toluene. So we've got that. Now let's see what all we need as inputs. First of all, we need to supply the temperature value, and we then need to supply our guesses for xb and xt. So what I basically did here is that I'm going to use a solver in order to solve this equation, and I'm going to supply the different values of temperature, the mole fraction of benzene in liquid and toluene in liquid, all 3 of these values as guesses. So, and what I want this function to return to me is the values of f0, f1, and f2. Looks like we need to call this f2 and not f1. So we have that, we run the function, and now what we do is I use the fsolve function that I imported from scipy.optimize, and I will supply our main function to function f to this, and I will also supply all of the inputs to this function as an array. So our temperature, I'll assume it's like 109 degrees. XB, let's say 0.2, and XT, let's say 0.8, because their sum has to be equal to 1. So let's run this and see what we get. So yeah, we got these values. So what this basically means is these numbers are the solutions to our problem. So the temperature has to be 109.13. The mole fraction of benzene is actually 0.173. And the mole fraction of toluene is 0.827. So this is how we solve a vapor liquid equilibrium problem